Welcome everybody. Today's topic is the study of the structural, electronic, and optical properties of pyrochlore type yttrium titanate by Omar Escamilla, Héctor Muñoz, Eliel Carvajal, José López, Raúl Escamilla, José Miguel Cervantes, Martín Romero, Jaime Antonio, and Paola Arevalo. Pyrochlore oxides with general formula Y2-V2-xZnx are an exciting group of compounds that exhibit a wide variety of physical and chemical properties. The crystal structure of pyrochlores can be considered as an interpretation of A and V three-dimensional networks of corner-sharing tetrahedral as it is shown in Figure 1. Polycrystalline samples of yttrium titanate with X equals 0.0, 0.1, and 0.2 were synthesized by molten salt method using yttrium oxide, titanium oxide, and zinc oxide. Phase identification of the samples was made with an X-ray diffractometer. The crystallographic parameters were refined using a Rietveld refinement program with multi-phase capability. Otherwise, chemical orbitals and valence band were measured by X-ray photoelectron spectroscopy. In Figure 2, X-ray diffraction patterns for the titanate are showed. Sample inset shows the shift of the peaks with 2 to 2 Miller indices towards larger angles with increasing zinc content. Moreover, in Figure 3, the refinement of the X-ray diffraction pattern corresponding to the yttrium titanate sample is observed. In summary, the reflections of the patterns of X-ray diffraction correspond to the pyrochlore type yttrium titanate. The patterns of X-ray diffraction then show secondary phases. The AL lattice parameter decreases, and consequently, the unit cell decreases as the zinc content increases, as it showed in Figure 3. Figure 4 shows XPS survey of the samples, while in Figure 5 there is a comparison of the XPS valence band spectra with density of states. Therefore, we can say the chemical orbitals were identified by XPS. A good correspondence between the XPS valence band spectrum and density of states is observed. A shift toward lower energies is observed in the XPS valence band spectra. In Figure 6, the optical band gap derived from the absorption spectra versus zinc content is showed. The optical band gap was calculated using the tau correlation. Optical band gap decreases with the increase of zinc content. Finally, in this work, we studied the crystal structure of yttrium titanate compounds. X-ray diffraction studies showed that the zinc 2 plus ion occupies the yttrium 3 plus sites, and as a consequence, the AL lattice parameter decreases, the valence band spectra increase at 0 electron volt, and the optical band gap decreases as zinc content increases.